Mathematics is, in its way, the poetry of logical ideas. And previously on Circle Geometry Theory Part 1, we discussed the logical ideas as it pertains to the circle, continuing the tradition of the Greeks, who would have explored the circle and come up with many different discoveries and ideas as it pertains to the circle. In that lesson, we would have first established a definition of the circle. It is a set of points or locus that are equidistant from a fixed point. Then we also looked at the parts of a circle. These are all names of the parts of the circle that you should be familiar with and know the meaning of when you see them in questions. Then we of course discussed the actual theorems of the circle. There are 8 theorems in all. We only looked at 4, 1, 2, 3, and 4. And after discussing them, we looked at how to apply them to questions such as this. So we are continuing to discuss the theorems of the circle. We're going to look at theorems 5 to 8 as a result. So here are the theorems 5 to 8. Let's just number them 5, 6, 7, 8 like that. We start with a line drawn from the center of a circle to the midpoint of a chord is perpendicular, that is at 90 degrees to the chord, right? So here is a line from the center drawn to a chord, okay? And a corollary of this theorem is that this line actually bisects the chord, and that is why you see these two dotted lines, these two dashed lines here, which indicates that they are the same length. All right, so one consequence of this line drawn from the center to the midpoint of the chord AC is that it would actually bisect the line, and therefore the length from here to here is equal to the length from here to here. Next, we have theorem 6, which says the angle between the tangent and the radius is always 90 degrees. Always 90 degrees. So here is the radius, this green line, and here is the tangent. Right? The tangent is that line that touches the circumference at one point. So if ever you draw a radius to a point of tangency, it's always going to intersect at 90 degrees, and that is what this theorem basically says. And next we have tangents from a common point, say A, right here, to a circle are always equal in length. So the tangents in this particular diagram is AC and AB. Again, we see those two lines, and they are put there to indicate that they are the same length. All right, so AB is equal to AC. Next, we have theorem 8. The angle between the tangent and the side of the triangle is equal to the interior opposite angle. So let's start with the tangent, this red line here. What you're looking at in the circle, well, we could call it a cyclic triangle, okay, because all the vertices of the triangle actually touch the circumference. All right, so that makes it a cyclic triangle. And when you are applying this theorem, just ensure that what you have is a cyclic triangle as part of the whole diagram with the tangent involved, right? So you will have a tangent, but if the triangle is not cyclic, then this theorem cannot really be applied. So first look for the presence of a cyclic triangle. So this diagram definitely has a cyclic triangle, and what it says is the angle between the tangent and a side, right? So let's look at this yellow angle here, is equal to the interior opposite angle. Now the interior opposite angle, how you would locate it is it kind of faces the angle in question, right? This would not really be the interior opposite angle because, well, it's kind of off the line. All right, this yellow angle is more, it faces this angle in a more literal sense. The angle between here, however, which was colored red as well, this faces the red angle here. All right, so it has to do with perspective. because when you're talking about opposite, you're talking about two objects actually kind of facing each other. So this yellow angle is facing this one, and this red angle is facing that one. But if you look at this yellow angle here, it's not really facing the red angle here. You kind of have to jump over this line and then go up the road here to actually see that angle, right? But here, this yellow angle has clear sight of the yellow angle here. So that's probably a way to understand it. The two yellow angles have clear sight of each other, and the red angles have clear sight of each other as well. That's just my puny attempt to make sense of the perspective, all right? But there are actually proofs which would establish theorems like this, so we could take it for granted that what they are saying here is true. All right, so these are the last 4 theorems of the circle, and we're going to now look at how to apply them to solve problems involving the circle. So as far as the practical use of these particular theorems, well, they are used for determining unknown angles within the circle, just like the previous 4 theorems, and they are also used to deduce unknown lengths. Theorems 5 and 7 specialize in doing that exactly, right? Because both theorems involve lengths, as you could see here with the 2 dashes. I don't know why I keep calling them dashes, but they're actually just short lines, right? These 2 short lines represent equality in length. So these 2 theorems can be used to deduce unknown lengths. So how about we dive in now and look at some problems to see exactly how we use these theorems to come up with answers for angles and lengths. So let us apply the theorems now to actual problems. We will start with this one. AB is a tangent to the circle. Calculate the value of x. So take a moment and pause this video and see if you could see if you can work out the value of x. Pause the video now. Okay, congratulations to those that would have worked this problem out. And those of us that just want to enjoy the show, well, the answer is pretty straightforward. It's just 43 degrees. Okay, how do I know it's 43 degrees, and how does those of us that got it correct know that it's 43 degrees? Well, we would have applied theorem 8, which says the angle between a tangent and the side of a cyclic triangle. Remember, I would have told you, ensure that you have a cyclic triangle in your scenario. We know that this one is cyclic because the vertices, all the vertices of the triangle touch the circumference of the circle. So it being a cyclic triangle, and we have this angle here between the yellow lines being 43 degrees, well, that will be equal to the interior meaning inside, interior opposite angle, right? So what angle is inside the triangle and opposite to x? Well, it's 43 degrees, so that x there has to be 43 degrees. Second problem, AB is a chord of the circle. TA and TB are tangents to the circle. So we see here TA and TB. You are asked to calculate the value of x. Go ahead and try that now. Pause the video now. Okay, congratulations to those that got this correct. You are a brilliant mathematician, and keep up the good work. And for those of us that probably didn't get through, or you're just waiting on me to give you the solution, well, I will gladly oblige. Okay, so first thing is TA is equal to TB. I know that based on theorem 7, because the tangents from a common point T, in this case, to a circle are always equal. So the common point here, T, forms this tangent here, TA and TB, and so based on theorem 7, those two are equal. But how does that help me to pursue the solution to the question? Well, I know now that triangle ABT is isosceles, right? Because an isosceles triangle, these two sides are equal, and with an isosceles triangle, you have two of the three sides being equal, and that would mean that these two base angles are equal. All right, so angle TAB and angle TBA, they are equal, and therefore I can calculate the size of one of those angles using this calculation. All right, so 180 minus 38 degrees divided by 2, that will give me 71. So the size of these both angles is 71 degrees, and therefore x is equal to 71 degrees. All right, so kudos to you math geniuses that were able to see all of this. I tip my hat to you. Third problem. Sometimes you have to let a wolf take down a wolf. So I would not ask you to pause the video here. Please do not shout for joy. All right. It's not that I don't think anybody could solve this problem. It's just that for time's sake, there are a couple things I want to just get through and, maybe just show you how to get this answer. Maybe there's somebody in this class that could work this out, but it's fairly complex, and I just want to show you step by step how to get there, because getting to the answer, getting to the value of y, is similar to like if you have to work out a 5-move checkmate in chess, or if you have a long journey and there's several turns and twists that you have to make before you get to the actual destination. And it's kind of like a maze, right? So some mazes you have to chart a course, you might bounce into a wall, and then you have to backtrack and try a different route, and sometimes it's like that. And even the solution to a maze, many times it's the path is kind of haphazard movement. It's never very straightforward. You have to go up, then down, then across, then come back, and then through. All right, so you get the picture. The solution to this problem is similar to that. But the first thing we need to establish or recognize from this diagram is that OD is a radius. And we will see why that is extremely important as we proceed in the solution to the problem. So OD is a radius because it's a line drawn from the center to the circumference. All right, so that means that the angle ODE is 90 degrees, as you could see the 90-degree box there. And why am I able to say that is because of theorem 6, which says the angle between a tangent and a radius is always 90 degrees. So that is why we needed to establish that OD is a radius. We were already told that DE is a tangent, so we could take it for granted that it is a tangent, and that set the stage to use theorem 6. So ODE is the angle ODE, that is 90 degrees. This means that triangle COD is isosceles. Why? Because of these two well, let me use some visual aids. CO, that line CO, is equal to that line OD. So they are both radii of the circle. So that means the triangle COD is isosceles, right? So this indicated by these yellow lines, that triangle there is isosceles. That means that the base angles will be equal, similar to what we saw in the previous problem, and therefore with the base angles known, we could work out this angle. And let me just let you know what the plan is. The plan is to work out the angle COD. That would enable me to work out the angle DOE, right? And if I could get the angle DOE, then I could use the fact that this triangle ODE, the sum of angles in any triangle is 180 degrees. I would have two angles at that point, and therefore I could work out y that way. All right, so even if you didn't follow exactly what I said, you can just follow now and just see what I said, right? So the first thing I would have said is to work out this angle COD, and it's worked out by this calculation here, which works out to 130 degrees. All right, so I've reached a crucial milestone in my journey to the answer, the value of y. I now have the value of the angle COD. It's 130 degrees. Now I could work out the angle here, because 180 minus 30 would be 50 degrees. All right, So as I would have said, by working out this angle, I was able to work out this angle, and now I have this triangle before me, ODE, right? And I have two known angles, 90 and 50. So I can add those two, subtract it from 180, and that will give me my y. So that is the calculation here. Y is equal to 180 degrees minus the sum of 90 and 50. That would give me 40 degrees with best work. Okay, so here you have it. All right, there you have it. This is the solution. Y is equal to 40 degrees. All right, and it was not what's the word? It was not a straightforward solution, right? There's several things that had to happen before we even get to the final calculation for the value of y. All right, so just take a while and look at, you know, the journey, the maze that we would have gone through to get to y equal 40 degrees. It was not obvious, right? So take note of this solution in particular, because when we get to the next lesson where we will discuss combination problems, well, the solutions would very much kind of flow in this way. So this is a preview. This is a sneak peek. All right, this is the trailer for the next lesson. All right, so I hope you're all ready. And we come to the final problem of today's lesson. This is AB is a chord of the circle of length 8 centimeters. We are asked to calculate the length of OB. Now remember, I would have pointed out two theorems in particular that I used to deduce the lengths of to deduce unknown lengths in the circle. So how about you pause the video now? This is not a wolf. I believe you could more than take this one down. Pause the video now and try to work out the length of OB. Pause the video now. Okay, so congratulations to those that have worked this out. You are doing very well in this lesson. All right, and again, I tip my hat to you. And for those of us that just want to enjoy the show and end with a bang, well, we start here. AD is equal to DB, which is 4 centimeters. So Martin, how did you get that? Well, remember I mentioned something about a corollary, and don't worry about this word. It just simply means an obvious observation that flows naturally from the logic of a theorem, right? So theorem 5 says a line drawn from the center of a circle to a chord would actually bisect the chord, all right? So that makes sense, because if this line here drawn from O to D, well, it hits the midpoint of the chord AB, and that means, well, if it's passing through the midpoint, then logically it bisects the chord AB. As a matter of fact, OD is the perpendicular bisector of AB. All right, so that's important to understand. So if it bisects AB, that means the length AD is 4 centimeters, which is actually half of 8 centimeters, and also DB will be 4 centimeters. So I could kind of put in these measurements here quite confidently, right? So with that in place, now I complete a triangle. Triangle ODB is right angle, and that is based on theorem 5, right? Do you remember what theorem 5 says? Right? It says, well, this is actually the corollary of theorem 5, but theorem 5 says basically that if you draw a line from the center to the midpoint, all right, it will intersect at a right angle. It would be perpendicular to that chord. So we use that fact to construct this right angle triangle. And do you see what's happening now? Can I determine OB? I can determine OB using Pythagoras' theorem. which says the square of the hypotenuse, which is OB, is equal to the sum of the squares of the other two sides. So that means that OB is equal to the square root of, well, 3 squared is 9, 4 squared is 16, and to get to OB you take the square root of both sides and you will end up with this calculation here. 9 plus 16 is 25, so therefore the square root of 25 is 5, and that means OB, the length of OB, is 5 centimeters. So this was another kind of problem where you couldn't get to the answer directly, all right, but you had to use your theorems to begin the journey, all right. So the first important deduction was to understand that AD is equal to DB and therefore is equal to 4 centimeters because OD bisects that line. After bisecting the line, you get this right angle triangle. Again, theorem 5 guarantees that. And then you use Pythagoras' theorem, you know, stuff that you learned in 4th form, 3rd form, I don't know. And then using Pythagoras' theorem would get you to the answer, the final answer. Okay, so we've come to the end of our study of circle geometry theory. The next lesson, as I would have said before, deals with combination problems in circle geometry. And those are the types of problems that you will see in exam questions. You would see these, the ones that we did in this lesson do appear in exam questions, but they don't appear by themselves the way you saw it in this lesson. CXC questions like to combine several ideas into one diagram. So in one diagram you might see this, you might see theorem 4, theorem 3, you might see a tangent. All right, they like to just superimpose so many ideas onto one circle, and you have to be able to recognize the different theorems that would be able to deduce the size of certain angles. So the next lesson I want to show you some tips, some tactics that you can use to recognize exactly what theorem to use, and even to just recall the theorems. Well, you have to know them by heart. There are 8 in all, and so from between now and the next lesson, please learn those 8 theorems, all right, because they are crucial for when you have to solve combination problems. All right, combination problems tends to be the type of problems that they ask in exam questions. So I want to make sure that you are prepared for that. I want to make sure that you have the experience of looking at a few problems and seeing how they are worked out. I will be asking you to pause the video in that lesson. All right, please do participate. Even if you get it wrong, it would help you a great deal. So until then, I hope you're all excited to go through that lesson. It's going to be full of some plot twists and some really exciting stuff. All right, so stay tuned, and in the meantime, keep working hard, and may the math force be with you.